Assalamualaikum. So we are still in the part about the image transform, and if you remember last time we have started applying some of the Fourier transform on some of the images, and we have applied it, if you remember, on a grayscale image. So today inshallah we'll apply it on a colored image, okay? And we'll see as well if, for example, we rotate the image, will it affect the resulting Fourier transform, for example, or not? If we, for example, we affect the image in the spatial dimension by rotation or something like this, will it affect the shape of the Fourier transform that we'll have or not? Then after that, we'll start talking about the wavelet transform, and we'll give you just a brief introduction about the wavelet transform. Then after that, we'll see how can we apply the wavelet transform on the images, which can be considered as a two-dimensional signal in space. Okay? So, to start, we will go first to the MATLAB. Let's see here, we have this one. So if you remember last time we have started with this image which is called the tower.jpg, and this image, if you remember, it was a color image that has RGB components, right? Okay. Then after that, what we have done is that we obtained its corresponding grayscale image. Okay. And for this grayscale image, we have applied the fast Fourier transform in two dimensions. Okay, so it was applied in the grayscale image, and here we have assumed that the size of the result of this, let's say, transform, it will be 1024 by 1024 pixels. So here, Control C, Control V. Also, if you remember, for the fast Fourier transform and for the Fourier transform in general, the result of this transformation, it will give me complex values. Okay? And also, here we have got the absolute value of the image. That's why here we are applying the absolute in order to get the magnitude of the values that you have, the complex values that you have. And this is the result of the conversion. If you want to see it in an image, it will be something like this. Okay? And if you remember last time we have explained why do we have such kind of shapes, right? So here we have said that we are trying to get the Fourier transform in two dimensions, okay, which is in the horizontal direction and in the vertical direction. And we have said that starting from this side, let's say from the left side, to the right side, here I have things that are repeating, right? So here from the extreme left to the midpoint, here I have the frequencies increasing, okay? Then after that, from the midpoint to the right side here, the frequency will decrease once again, okay? So around this midpoint, each 2 points that are equally distant from the right and the left, they are complex conjugate to each other, okay? They are complex conjugate to each other. And the same thing can be said for the vertical direction. Okay? So in order to make things easier to understand and to see and to perceive, what we have said that I have a function that's called FFT shift. Okay? Which will divide this, let's say we can call it a figure or something, it will be divided into 4 quarters, and these quarters will be swapped together. And the result of this swap will put the zero frequency at the center, and as we go away from the center, the frequency will increase. Okay? So here we have this function, which is called FFT shift, and this is the result of its display. So we'll have something like this, as you can see here at the center, which is the bright part. This corresponds to the low frequencies, and as we go away from the center, the frequency is increasing. Okay? Of course, if this image is noisy, if this image is noisy, what do you expect to have as a difference between this Fourier transform of the original image and its noisy version? Of course, here I will have more white pixels, but this, or white points, but these white points will be situated where, in fact? That corresponds to the noises. Actually, they will be near the borders, okay? It will be near the borders. This means that it will correspond to the high frequency components, right? So as you can see from here, if I have a Fourier transform of my image, I can make some sort of filtering, okay, by applying, let's say, a mask on my image, okay, by allowing only the frequencies that appear near the center, and I can suppress the other frequencies that appear at the high components. Then after that, I can get the inverse Fourier transform. Okay, so like this, I have removed the high frequency components. We'll see some examples of this, inshallah, next chapter. Fine. Let's see here, for example, if I want to make the first Fourier transform on the color image directly, which is called image X. Okay, and I will get its absolute value, and I will get the FFT shift. It will be. Okay, so here in this capital Y, actually, I have the result of the first Fourier transform of the color image. Okay, what will happen here actually is that the first Fourier transform will be applied on the separate layers, layer by layer. Okay, so this means that the first Fourier transform will be repeated 3 times. Okay, and here just for the sake of illustration, these are the different first Fourier transform of the different layers, as we will see here. Okay, so this is the result of the first Fourier transform for the blue component, or for the, let's say, for the blue layer. Okay, and we have another one for the green, and we have another one for the red. Okay? Right? They will be? No, they are not identical all the time. Okay? They are not identical all the time. So, because actually, if I have a combination of colors, okay, the appearance of the red, okay, is not, it doesn't have the same, let's say, appearance of the green or the blue. They will only be identical if the image is a grayscale image. Otherwise, it will be not identical. Okay. So the rule here is that the first Fourier transform of the 3 layers are not identical, except in certain special cases. If, for example, the image is grayscale. Okay. Fine. Now let's look at another example here, which is example number B in your book, in chapter 5. Here, let's consider the following. I have the original image, okay? Here I will use the grayscale image that I have created, okay? And I will rotate it with 30 degrees. And I will get the first Fourier transform of this rotated image. What do you expect to see in the resulting transform? Will it be affected? What do you think? Okay, so here actually we have an argument now. Okay, some of you have said that it will not be affected, others said that it will not be affected. Let's see here what will happen. So this is the result of what we call it, the rotation. Okay, what I will do actually here is that we will get the first Fourier transform for this image. Okay, so what do you expect to see here? Let's try it and see. So here we'll get the first Fourier transform and get its magnitude, its absolute value. And let's see here what will be the result. This is the result before making the shift, before making the FFT shift. Okay, so it will be something like this. So as you can see from here, any special transformation, whether, for example, it's a rotation, especially the rotation, will affect the resulting Fourier transform. Okay? And of course here, in order to make things easier, we will do the shift and display the shifted image, Control C, Control V. Okay, so to do something like this here as well, the center point here, it corresponds to the low frequencies, and as we go away or further from this point, the frequency will increase. Clear? Okay? Right. So this is for the Fourier transform. What we'll start discussing now is about the wavelet transform. What is the difference between a Fourier transform and the wavelet transform?
Fourier transform is always sine as the fundamental frequency.
Yes.
While wavelet is
In the wavelet we have?
fundamental frequency is not always sine.
Yes. So here, let's consider that I have a waveform like this one. Okay? Okay? And I want to get its Fourier transform. The Fourier transform, as we have said, so in general, any transform is that I will multiply the original signal with a certain, let's say, basis function, and I will get its average, or let's say its integration along all of the time, let's say from negative infinity to positive infinity. Okay? Here in this case, for the Fourier transform, what is the shape of my, let's consider the basis function here? It's a sinusoidal signal, okay, that extends from negative infinity to positive infinity. Okay? Right? But the idea here for this original signal, its frequency, as you can see, it changes with time. So here, for example, I have very low frequency, and after a certain period of time, the frequency has increased. Then after that, the frequency has decreased again. So I want to trace this kind of changing. Okay? Using the first Fourier transform, or the Fourier transform in general, it will not capture this information. Okay? So that's why here we use the wavelet transform. So here, what will be the basis function for the wavelet transform? Instead of the sinusoidal signal, I have several types of wavelet functions. We have something that's called the Buch's. We have something that's called Haar, or H-A-A-R. Okay? And we have something that's called Montlin. We have several types of, let's say, wavelets. Okay? But this wavelets, it can have this form. Okay? This is not a nice wavelet. Okay? Right? And as you can see from here, the wavelet, this is the basis function. And as you can see from here, that the wavelet function, this is called the mother wavelet. Okay? If we compare it with the basis function of the first Fourier transform, we'll find that it is restricted, or let's say it is confined within a certain period of time. Right? So this means that the signal will start here and it will end here. Before this point, the value is 0, and after this point, the value is 0 again. Okay? So what will happen here in the wavelet transform, we'll find that it analyzes according to something that's called what? Scale and or resolutions. Okay, we'll call it resolution. Together with something that's called translation. Okay? So here, this is the formula that we use for the continuous wavelet transform as a function in two things. For the first Fourier transform, the resulting wave that comes from the transform is function in what? It's function in frequency. Okay? It's function in frequency. But here, actually, it is function in two other things. Okay? Actually, here it is function in A here. This is called the scale. And B here is called what? The translation. Let's look at the equation that we have here. I will assume that the continuous wavelet transform, I will represent it with capital Psi, like this one, of A and B, where A here, as we have said before, is the scale, and B is equal to the translation. And you will see what is the meaning of scale and translation here. This is my function that I want to transform, x of t, which will be, in this case, for example, our image as a function in distance. Okay? And this psi star of t minus b divided by a, this is the basis function. Okay? Where a here is the scale factor, and b here is the translation. Okay? Fine. Here, this A and B, how they will vary? How will they vary? So actually here, if A is equal to 1, let's say, I will have this wavelet. Okay? If A, for example, is greater than 0 and less than 1, this means that A is less than 1, it has a fractional value. What will happen here in this part is that the function will change its resolution to be something like this. Okay? So this means that here the frequency will increase. Okay? So this means that I'm dealing with the same, let's say, signal, but the signal now is compressed with respect to time. Okay? So this amount of changes, instead of happening, let's say, during a period that is equal to T1, here it will happen during a period that is equal to T2, where T2 here is less than T1. So here the frequency has increased. By increasing the A, the scale, the frequency will increase. If A decreases, frequency increases. Okay? But if I have an A that is greater than 1, what will happen to this signal? Actually, here the time will be longer. So actually, I will have these variations. It will take longer time. So this means that the frequency here will decrease. Right? Okay? So this is for what? This is for the scale. So here I'm scaling this wavelet with respect to the frequency. But what about the translation? Here the idea is that by varying the value of B, I can change the position of this wavelet to the original signal that I want its, let's say, wavelet transform. So for example, if I want to get the transform for this part that corresponds to the low frequency, I will put the B with a certain value, let's call it مثلا B1. Okay? If I want to get, let's say, the analysis of this signal within this part of frequency, so in this case I need to move this wavelet by changing the value of B to B2. So in this case I will have something like this, and the position of the mother wavelet actually will be in this position with respect to the original signal. So like this I am analyzing this part. Okay? So by using this wavelet transform, I can make some sort of localized analysis of the signal by changing the translation, and also I can make some sort of, let's say, for each part of this signal, I can make analysis for different values of frequencies by changing the scale. So like this, I'm changing two things. I'm changing the scale to change the frequency, like in the case of the fast Fourier transform. I'm multiplying by a sine signal, sinusoidal signal that has variable frequency. How can I change the frequency here in the wavelet transform? By changing the scale, the A. Okay? And since this, let's say, wavelet, it has a certain limited range within which it has a non-zero value, otherwise it has a zero value. So I can change its position with respect to the original signal by making a translation that is equal to what? To B. T minus B, this means that I have translated the signal B units in the time domain. Clear? So like this, I can make an analysis, much more realistic analysis of this signal. Okay? Much more realistic analysis of this signal. Okay? And as a result of this, what will happen is that if you look at the resulting, let's say, wavelet transform, I will have something like this. It will be time against frequency. It will be time against frequency. So at this point of time, I have this level of frequency. And at this point of time, I have this level of frequency. Then after that, the frequency will decrease again at this instant of time. This is something that does not exist in the Fourier transform. Understand the idea? Okay? So in the Fourier transform, the resulting signal, it will be something like this. Here I have frequency, and here I have the amplitude that correspond to these frequency components. Okay? Here, if you want to understand this, let's say, figure, this figure actually it is a three-dimensional figure. It's a three-dimensional figure. This means that at time t, I have this frequency component. But what about the value of this frequency component? It will be something that corresponds to a height that comes out from this, let's say, picture. Do you understand the idea? So here, instead of having just two components, which is the frequency against the amplitude, here I have the frequency and amplitude and the time as well. Clear? Time. Yes? And time, yes.
Time that is frequency.
In our case, for the images, instead of time, I will have a space. I will have, for example, the row, and I will have as well the colors. Understand the idea? So you're actually, this is the time, this is the domain from which I want to make the transform. In our case, I don't want to make a transform from the temporal domain, I want to make a transform from the spatial domain. So in the image, this time it will be replaced by the position, by the space. Okay? Do you have any question about this part? I don't want you to memorize this formula, I just want you to know it, okay? So here, when we talk about the scale, again, which is the value of A, it is used to dilate or contract. Dilate, this means that I will stretch or contract the wavelength. Okay? By contracting, this means that the frequency increases. And by dilation, this means that the frequency decreases. Right? And here, as we can see, that this scale A is directly proportional to the frequency to the power -1. It's inversely proportional to the frequency. Increase the scale, decreases the frequency. Decrease the scale, increases the frequency. Okay? Right. Here, how can I increase and decrease? By using the scale value. So here, if scale value is less than 1, this means that the frequency will increase. It's high frequency. If A is greater than 1, dilation occurs. So here, in this case, I will have high scale, so I will have low frequencies. Okay? Right. Also here, we talked about the translation, right? And here by the translation, I mean the shifting of the wavelength with respect to the original signal that I have. Okay, by the value of B. Okay? So here we say that this continuous wavelet transform, or the wavelet transform in general, it will result in a relationship between frequency and time. It will result in a relationship between frequency and time. So this is what's meant by time frequency tiles. You know what's meant by tiles? Okay? So here I have the time, and here I have the frequency. Okay? And we have a principle. I don't know, did you study before this Heisenberg's uncertainty principle? Did you study before the wavelet transform?
Yes.
Very good. So here for this uncertainty, it says the following. We say that we can have either high frequency resolution and poor time resolution, or poor frequency resolution and high time resolution. Okay? So here we say that when we talk about low frequencies, in this case I will have, it is better to, let's say, to analyze the signal in the frequency domain. Because in low frequency here I have higher resolution. From where did I get this? If we apply it, for example, to the hearing system of the human being, you will find that in order for the human ear to distinguish between the different frequencies, for example, if the human ear can distinguish the frequency F, okay, it will start distinguishing, let's say, the higher frequency starting from 2F, okay, and from this 2F, it will start distinguishing the higher frequencies starting from 4F. So like this, as you can see here, the frequencies are increasing by something that's called what? Octave. Okay? Each time the frequency is doubled. So as you can see from here, that at low frequencies, okay, I can have better resolution than at high frequencies. But what about these signals that are having high frequencies? Which domain is better to analyze them? It would be in the time domain. Understand the idea? So this is something that is related to signal processing. Yes? The blue?
Yes.
The blue tiles. Here, the blue tiles, this means that this part of tiles, you can analyze it whether in time or frequency. Because here, as you can see, the width, here it represents the resolution. Okay? The smaller the width, this is the better the resolution. Okay? So as you can see from here, smaller the width of frequencies, actually this happens at low frequencies. Okay? And smaller resolutions of time, actually this happens at high frequencies. Okay? Or let's say better resolution of time, this happens at high frequencies. So with this tiles here, it represents this part in the time frequency space, okay? what are the resolution of the time domain with respect to the frequency domain. As you can see from here, this red one, for example, the resolution of the frequency is better than the resolution of time. But if you look at this one, which is the yellow one, here you will find that the time resolution is better than the frequency resolution. Okay? Here for this blue one, the resolutions actually are incomparable. So either you can analyze the signal in the time domain or in the frequency domain, it doesn't matter. Okay? Right. So they are showing us some of the applications that we can do using this wavelet transform. One of the things is denoising, okay, of noisy signals. And this is the image of somebody that's called Ingrid de Botches, okay, which has its mother wavelet by her name, okay, de Botches. So here he's showing us, for example, this is the noisy close up. I don't know whether it's clear or not. This is the noisy close up, and this is the denoised. Okay, so after applying, let's say, this kind of transformation, we can apply some sort of denoising techniques. So I will have images that are relatively less noisy than the original ones. Okay, we will see, inshallah, in the next chapter how can we do this type of denoising. Okay. Another thing here, we have said that one of the most important applications of this kind of image transforms is the compression. Okay? So as you can see from this image, if this image is to be divided into two parts, here we have the left part and the right part. And here we say that this is the original image on the left part, and this is the image after compression by a ratio of 100 to 1. As you can see here, with respect to the quality, you cannot recognize much difference, although we have made some sort of high compression here. Here also he is referring to some kind of comparison between the wavelet compressor and the JPEG compressor. This is the wavelet, this is the JPEG. Okay? And so on. Right. If we look at this expression, this is the same expression of the transform, but in a discrete system for 2 dimensions. Okay? For each dimension, I will have a scale and the translation. So that's why here for dimension, let's say in the rows dimension, let's assume that in the rows dimension, I will have a scale A1 and translation B1. And in the column direction, actually here I will have scale A2 and translation B2. Okay? And then instead of the integration, in this case I should have double integration. Instead of double integration, here I have double summation because this is a discrete function. Okay? And this is the expression that we have for the wavelet transform. This is the original image, f of mn, and this is the result of the transform. And this is the inverse of the wavelet transform. Okay? So this is the transformed image, and this is the resulting image from the inverse wavelet transform. Okay? And this is called what is called discrete wavelet transform. Discrete wavelet transform. And this is the type of transform that is applied on images, in fact. Right. The technique that is applied for the transform, we can look at it in this way. Here I have, this is the original image, and this is the result of our, let's say, conversion. And of our conversion here, it will result in 4 images. Okay, it will result in 4 images, where the total size of these 4 images actually is equal to the original image. So for example, here if I have an original image of size m by n, okay, this is the original image, the result of the transform it will have m by n, but it is divided into 4 equal parts. Okay? Where here, the first part here, we call it the approximation. Okay? Here we have, this is the vertical detail, we call it like this, vertical detail. This is horizontal detail. And this is the diagonal detail. Okay? And the size of each one of these components actually is m over 2 by n over 2. Right? This approximation, we can look at it as if it is the result of applying low-pass filter on our image. Okay? So here, if we look at this part, we will find that here is putting names like low-pass filter, high-pass filter, etc. So actually here I'm applying on this image different types of filters applied in different directions, either in the horizontal direction or in the vertical direction. Okay? So here, if we talk about the original image, in the first step here, I will consider the rows. Okay? So this same image will be applied on a low-pass filter with respect to the rows, and to the high-pass filter with respect to the rows as well. Okay? And this will result in something that's called, the output of the low-pass filter here is called horizontal approximation. Okay? And the output of the high-pass filter is called horizontal detail. Okay? So as you can see from here, this horizontal detail, it will give you where in the image you have high-frequency components. Okay? But in the horizontal direction. Okay? Then after that, the output, or let's say each one of these two images, here I have horizontal approximation and here I have a horizontal detail. Then after that, in the next stage, I will consider the colors. And each one of these images will be applied on a low-pass filter in the vertical direction and high-pass filter in the vertical direction. Okay? So if I look at the approximate image here that appears here at the top right corner of our image, or our slide here, we'll find that this image, it has passed through the low-pass filter with respect to the lows, followed by a low-pass filter with respect to the colors. This is called an approximation for the whole image. Okay? This means that the high frequencies in this component actually have been suppressed. Okay? If we look at this second one here, which is the second block from the top on our right side here of the slide, it is called vertical detail. This vertical detail, it results from, as a first stage, it has been passed through the low-pass filter applied on the rows. After that, followed by a high-pass filter applied on the colors. So like this, I can see the vertical detail. Okay? Here for this one, which is the horizontal detail, it has passed through the high-pass filter with respect to the rows, followed by low-pass filter with respect to the colors. Okay? And the last one here, which is called the diagonal detail, it has passed through the high-pass filter of rows and high-pass filter of colors. So it will show me what will be the variation of the frequencies in the diagonal direction. Okay? Which is the resultant of the horizontal and the vertical high-pass filters. Okay? In order to make things easier, let's assume that I have something like this. So as you can see, if I have an original signal, it will result in this 4 different components. Right? It will result into this 4 different components. Right. Here, as you can see, LL1, this means the result of the signal after passing through low pass filter for the rows, followed by low pass filter for the colors, which is the approximation, let's say, image. We'll find that this image is somehow similar to the original image, but with a smaller scale. Okay? Where the width and the height will be half the width and the height of the original image. But for the other 3 images here, it will give me the frequency changes that will happen. Or let's say the frequency components that exist in this image. In the, let's say, here this is high, so this will be in the horizontal direction, this will be in the vertical direction, and this will be in the diagonal direction. Okay? So this is one level of analysis. Can I make further level of analysis by making, let's say, scaling instead here to obtain this signal? What happened is that I have changed this scale by 2. Okay? Can I make further analysis of this signal? Yes, I can make further analysis of the approximation part. So here, as you can see, this LL1 part, it can be divided into another level or another level of scale, okay, to obtain LL2, HL2, LH2, HH2, and so on. And this can proceed, as you can see. Each time I will take the approximation component and I will make further analysis of it. Okay? It depends on what type of analysis I want to do. So, this is another let's say, a figure that shows what happens actually. Here I have the original image, right? Low D, this means that this is a low filter for the decomposition of the image. I want to decompose the image. Okay? And this here I have high filter for the decomposition of the image. Both of them are applied on the rows. Then after that, here I will make down sampling. Okay, so this means that the scale actually will be decreased. Then after that, the resulting image, I will apply it again to low decomposing filters and high decomposing filters in the direction of the columns. In order to obtain the LL, which is the approximation, here I have, let's say, this is the vertical detail, this is the horizontal detail, and this is the diagonal detail. Okay? So this is for the decomposition. Now if we talk about how can I, given a decomposed image, I want to restore the image back again. Actually here I will use another type of filters that are called restructuring or restructuring filters. Okay? Or restoring filters. Here we have low, high, and I will apply the filters in the opposite order that we have applied before. And in this case, I will have an upscaling instead of downscaling. Okay? And in this case, what will happen is that at the end here, I will have an approximate image, which is the result of the inverse transform of the wavelet transform. Actually, here I don't want you to enter into the details how this will happen. But what we are going to use here in our course is that we will use this type of transformation to do or to obtain, let's say, the wavelet transform of our images. And after that, we can see what we can do with it. Okay? So the image that we will apply our transformations in is this one. Okay, here as you can see, this is an American football ball, right? And as you can see here, he has put this, it was selected in a way so that this part, as you can see, it can show me what will be the horizontal details, right? Because going from this blue, that color to the white color, this will result in an abrupt change. So this means that here I have a high frequency component in this area, in the diagonal direction. Okay? So, if we apply our, it's not very clear. Anyway, so we'll consider it something like this here. This is the approximated image. As you can see here, it is half the image in both directions, in the rows and in the columns. Okay. This here we have, it shows mainly, it should show the horizontal variations. Okay, the variations in the horizontal that appears as horizontal lines here. Okay, so actually here the filter is to be applied in this direction. The high pass filter is applied in this direction. And the low pass filter is applied in the opposite direction. So here we have, this is the high, and this is the low. If you are applied on this part, I will find that this is the low, and this is the high. So this is below, and this direction is the high. Okay, here we have this is high, and this is high. Right. So if we are going to apply the high pass filter in this direction, this means that it will detect the horizontal lines. Okay, it should detect the horizontal lines, or let's say the variations that appears in the form of horizontal lines. For this one, it will detect something like this, vertical lines. This one, it will detect the diagonal lines. Okay? So here it will detect, let's say, the variation of the frequency in this direction, which is in the direction of the columns, the direction of the rows. This one is detect the high frequency changes in the direction of the columns. And this one, it is the combination of both, which will give you the variations in the diagonal direction. Clear? Okay. Right. If I want to make further analysis of this signal, what I should do with another scale? I should use which one in which part? The approximation. And this approximation will result in another 4 small, let's say, rectangles. Okay? I think we have something like this. Result in something like this. Okay? And as we go further in the different scales, what will happen is that I will have further analysis of my signal here. Okay? Let's look at how this can be applied in. Yes, I need to use this one. No, after that, actually, we need to make some further processing in order to make the noising of this thing.
Because each time we are taking the low frequencies.
Yes.
Right?
Yes. Because actually, here what you will do, in fact, in order to denoise this signal, you will start handling the vertical, horizontal, and the diagonal details, and try to suppress the high frequency components that appear here. See what I mean? So here, actually, what you can detect is that in the let's look at this signal here. نرجع تاني. Yes, we need to discuss this signal. Let's take the other one here, the previous one. Okay, so this is the result of applying the discrete wavelet transform for one step. Okay, this means that I have downscaled once. Okay, fine. A question, a very important question. If I will apply the fast Fourier transform, okay, is there any relationship between what I have here with what will be resulting from the fast Fourier transform? There is no direct relation, right? Okay. In the fast Fourier transform, I have frequency against amplitude. But here I have frequency, okay, against position, against amplitude. Okay. So from here I can know where exactly in the figure I have high frequency components, and I can suppress it. Okay? So for example here, let's assume something like this. If I'm sure that this point, this white point, is a noise point, okay, in order to denoise this signal, what I should do here in this case? Change this value to as minimum as possible. You see what I mean? So like this, the information that you will have here from this wavelet transform is totally different from the information that we had from the fast Fourier transform. Okay? Here it is somehow richer. Okay, I have more rich information. I have an information about the frequency component, its value, in addition to its position in the image, where it exists. So here when I find, for example, a high frequency component in a certain range, so this means that either this is an abrupt change in the image itself, like for example here, if you remember the central white part of the ball, okay, here I have high frequency, abrupt change from the red color to the white color. Or it can represent a noise point. Okay, so it's up to me how to handle this information. Now I have the information as a function of frequency amplitudes against frequency and space. So I can change the values in any way I want. Either, for example, by multiplying it by an attenuating factor or something like this. You see what I mean? Okay? So in this case, the way of handling this type of images or this type of transforms is somehow different from the way that we are going to deal with in the case of the Fourier transform, as you will see in the next chapter. Okay? Clear? So this is a very important thing to understand here. Okay? This gives me an information about the frequency components, the high frequency components, etc. But it is totally different from the result that comes from the fast Fourier transform. Totally different. This one is much more rich in information. I have the amplitude of the frequency, and I have the value of the frequency in addition to its position in the image, where I find it here in this image. Okay? طيب بسم الله الرحمن الرحيم. Here we have this. Okay, so here I have a problem with my MATLAB. We'll make a copy of this one. Okay. Control C. Okay, so this is the image that we will deal with, which is called football.jpg. Okay. And then after that, in MATLAB, as you can see here, I have this function which is called DWT2, which is discrete wavelet transform in 2 dimensions, right? Here I can provide it with the image that I want to analyze, okay, together with the type of the mother wavelet that I want to use. So this mother wavelet is called the Butches. The Butches in 2 dimensions, okay? Or we can use the Haar wavelet, which is HAAR, okay? And so on. The Haar, of course, is the simplest, but the Butches here is very rich, okay? Here, as you can see, what I'm trying to do here, I'm applying this wavelet transform on what? X here is the color image, but here I'm applying it on X, colon 1. So here it is applied on what?
The red one in the red.
Just the red layer. And I will apply it on the green layer, then after that I will apply it on the blue layer. Fine. What will be the output of applying this kind of transform? As we have said before, this kind of transform, it will result in 4 parts, okay, 4 components. We have approximation, we have the horizontal details, we have the vertical details, as well as the diagonal. So these are exactly what we will have. Okay, here we have this is the approximation. A here stands for approximation. X, this is the name of the figure. A is the approximation, okay, for the red component. And this is X, horizontal detail for the red component, vertical detail for the red component, diagonal detail for the red component. The same thing will be applied for the green and the blue. Right? Okay? Take care of these dimensions here. X, the original dimension is what? 579 by 190 by 3. But if I have these values, what do you think about the dimension of XAR, for example? It will be divided by 2 with respect to the rows and columns, and it will be 1 layer. Right? Okay? So here, if we take this, so we'll take this line here. So as you can see, this is the dimension of the X, 156 by 120. The XAR, which is the result of the first, let's say, conversion with the scaling down here, it will be 129 by 161, which is approximately half the dimension. Okay? And the same thing for the XDR, and same thing for the XVR and XHR. Right? So here we'll repeat, this is done for the red layer, as we have said before. We'll repeat it for the green and for the blue. So here, when we go back, Control C. Okay. طيب. As you can see from here, now we will try to get the approximation component and reconstruct it again from the red, green, and blue component, right? And for the horizontal details, we'll get it from the horizontal of the red, green, and blue, and the same thing for the vertical and for the diagonal, right? Okay. Then after that, I will try to put all of the 4 figures together in one figure by constructing a matrix like this one. Once I find the approximation, here I have the vertical detail, the horizontal detail, and the diagonal detail, I will put it in a matrix, okay? Such that in the first row, I will have the approximation together with the vertical detail, and in the next row here, I will have the horizontal detail with the diagonal, okay? So we'll do something like this. Let's see. Okay, so this is the result of the transformation. Okay, as you can see, this is the approximation followed by the vertical, this is the horizontal, and this is the diagonal. Okay, of course, here on the data show does not, you cannot see the differences, but if you run it on your machines, things will be much clearer.
So this is for the red?
Yes? No, this is for all of the components actually. Okay, this is for all of the components that you have here. طيب, let's look at. Actually, here log10, you don't need the log10. In this case, you can use directly the values that you have. ما لهاش سبب يعني منطقي. But here you need to, يعني since it's a double, just make sure that the maximum value will not exceed 1. It's not a subplot. It's not a subplot. We're not using the subplot, but we are creating a matrix that consists of 4, let's say, rectangles. Okay. First one represents the approximation, the horizontal detail, vertical detail, and diagonal detail. Okay, and they are concatenated together. That's it. Okay, it's not a subplot. Of course, you can do it using the subplot. You can do it using the subplot. But here, actually, it is very primitive. Here. I'm just putting the images side by side in one matrix and displaying it as one image. Okay. طيب. For the let's look at. Then after that, in the remaining part of this example, he's trying to do the same analysis again, but on the approximation part. That's just the approximation part that we have. Okay? So I want you to test this at home. Okay? I want you to test this at home. So at the end, after testing it and running this part of the code, you should have something like this. Okay? As you can see, as a result, for the first level or for the first scale, you obtain this one. In order to get to the next scale, I will get this one. In order to get another scale, actually this rectangle, it will be divided into another, let's say, 4 small rectangles and so on. Okay? For the time being, we have just seen how can we make the transform, but we did not use it yet. Right? So in this chapter, we are just introducing the transform. Afterwards, we'll see how can we use it. Okay? A third transform in this chapter that we will deal with is called the Who transform, which is used for the identification or the recognition of shapes. So here we have. So how this Who transform will be used in order to identify shapes of things? Actually, here we are depending on the geometrical properties of the shapes that we want to identify. Okay? So for example, here we'll take the simplest case, which is the identification of lines. I need to identify whether I have lines in this figure or not. And if I have lines, I want to identify them, and I want to identify their positions and other things. So, Let's consider something like this. Assume that this red line, this is the line that I want to identify. Okay? Its equation can be written like this. It is rho that is equal to m, where m here is the horizontal axis, cosine theta, where theta is this angle, which is the angle that is made by the line perpendicular from the origin to the line that I want to identify. Okay? Plus n, which is the value that appears here on the vertical axis, sine theta. Okay? Sine theta. So actually, any point here that has m and n, it should follow this expression. Okay? It should satisfy this expression. I don't know whether you studied something like this before? But we want to prove it. I want to prove it. Here we can say that rho here is a value that represents the distance between the origin and the line itself. So as you can see, this blue line is a line that is perpendicular, that comes out from the origin, perpendicular to the red line that I want to detect. Okay? And rho, it is the distance of this, or the, let's say, the length of this blue line. And theta is the angle that is done by this blue line with the positive x-axis. Provided that theta here, the positive direction of theta is in the counterclockwise. Okay, so this is positive theta. Now let's take any point here. Let's consider the point here, which is the point of intersection between the blue line and the red line. And I will call this point to have the value of m and n. And I want to see here, if I put m and n here in this equation, will I have rho is equal to m cosine theta plus n sine theta or not? Okay? So, how can we do this? First of all, this distance is m, right? And this distance is n, okay? Clear? Okay. Now let's look at something like this. Who can tell me how can we prove it? That rho is equal to m cosine theta plus n sine theta. I'll give you a hint. Take, let's say, a perpendicular distance from this point here. Okay? To this part. Right? This distance here and this distance here. Rho actually is equal to the summation of these two distances. Right? The first part here from the origin to this point, let's call this point مثلا S. From O to S, what is the length of OS here? It's m cosine theta. Okay? And what is the distance from S, let's say, to T? Okay? It is equal to n. This is n, provided that this is the angle here. In this case, this will be theta. So it will be n sine theta. Right? Okay? Take care of something, that this triangle here is right angle triangle, and this one as well is right angle triangle. So the ST as well is what? Is n sine theta. And since rho is equal to OS plus ST, this means that it is equal to n cosine theta plus n sine theta. Right? Okay? Right. Is it applicable to any other point here on this line? Should we have the same relationship? Let's try it. Take, for example, another point here. First of all, do you understand this part? Okay? So we'll just... Okay. Did you finish? Finished? instead of taking this easy point, I will take another point here, any arbitrary point on this line, and call it as well what? M and N, right? And here I have, this is the distance N, and this is the distance N. And I want to see here whether this relationship holds again for this arbitrary point or not. What do you think? Yes. Mm-hmm. So using the same rho and the same theta, actually this equation should hold. Okay, should be satisfied. So what do you think? How can we do it?
We can use the triangle.
Yes. Which triangle? Okay. Tell me here, which triangle you mean?
This one. Yeah, this one.
This one? You mean this one here? Yes. قصدك دي مش كده؟ طيب. Okay, how can we use it? Okay. Any ideas? خلينا نعمل كده as we have done before. Okay, let's take from this point, take a perpendicular, and see whether this will help us or not. Assume that this is the point we call it what S, and this is the point T. Right? Okay. So. So then OS is again equals to what? M cosine theta. But what about ST? If I make something like this. Okay, this is N, right? Not good. And this is angle theta, and this is right angle triangle, right? So this distance here is equal to how much? N sine theta. What is the relationship between this distance and the ST? They should be here, and the figure is not exactly, it is not perpendicular 100%. But this line and this line actually they are equal. Okay? Right? Here, if I will take this part here, it should be a rectangle. Okay? So this, each two opposite sides should be equal. So this distance from ST is equal to this distance, which is N sine theta. So if you take any point on this line, it should satisfy this point. Okay? But how can I make use of this property to define that I have a straight line like this? What do you think? First of all, do you understand how did we obtain this relationship for the straight line? So our question now is how can we say, or how can we use this relationship in order to specify or to identify the straight lines that we have in our image? Actually, in order to do such thing, first of all, I will not be able to apply it on the colored images or even the grayscale images directly. I should have a step before, which is called edge detection. Edge detection. So, for example, I will apply it, let's say, on an image like this one. Okay? Here, as you can see, where are the straight lines in this image? This is a very simple image, as you can see. Okay? Here, for example, I have this is one straight line. Okay? I have another straight line like this. Okay? I have another straight line like this. So here in this case, actually, I have 4 straight lines. Okay? Still, using this image, it is not easy to define it. So first of all, I need to identify the edges. And after identifying the edges, I want to see whether this edge it will form a straight line or it is in the form of a curve. Okay? So as a result of this, if we apply the edge detection, I will have something like this. Okay? Once I have applied the edge detection algorithm on my image, the resulting image, after that I will take this resulting image, okay, and I will try to find something like this. I will transform the image from, let's call it an n space to theta rho space. Okay? And for each n here, okay, I will apply to this equation. Okay? Let's say مثلا here, for each value of theta, I will apply the n, okay? And I will see the result. If this n, let's say مثلا here, of course here I will select the n that corresponds to the white line. Okay? That corresponds to the white pixels. I will select the n's that correspond to the white pixels. And I will substitute here. Okay? And see what will be, for the different value of theta, what will be the value that corresponds to the rho. Okay? And then after that, we will see, this figure, it's 3-dimensional. Each time, for example, I have a value, let's say, مثلا here, when we apply mn, this mn, for this value of theta, I have this rho. Right? If I have, for example, this mn is on the same line, if I will apply this new mn, this n1, n2, n2, if I will apply it again in this expression, it should be on the same point, since it has the same theta and the same rho, because they are coinciding over the same line. Okay? So as a result of this point here, I will have a counter. Each time I will have a hit, the counter will be increased by 1. And after I finish with all of the points that I have, I will track here what are the values of rho and theta that are having values greater than a certain threshold. For example, here I have a threshold, let's say, of 100. Here I have 102, here I have 200, here I have 300. Okay? So this means that this figure consists of 3 lines. You understand the idea? So we'll make the analysis, inshallah, next time.